Okay, so good time of day, everybody. I know that it's early morning for some, it's late night for others, and if you're watching this in the future, who knows what time it is for you. Um, the idea here is that we're going to go through some geospatial processing in Python, mostly using Geopandas, or pretty much entirely using Geopandas. And yeah, this is just an introduction. Unlike some of the other tutorials, I didn't write any of the actual tools that are being used here. I just am a little bit further down the path of using them than some people who might be watching this, and that's really all. Um, so if we switch to a screen, you'll see that the GitHub repo is here, ntb-za transform-2020-spatial-in-python. There is also on the Swang channel, there is a link to this. This tutorial is part of Transform 2020, which is being run by the Software Underground, which, yeah, it's a Slack channel and newly incorporated nonprofit for doing cool stuff with, computers and geoscience, with a focus on subsurface geoscience. So there's a lot of people hanging around who do geophysics and things like that, but we're fairly egalitarian about that. So, if you have an interest in geoscience and computers, then come join us. And on that note, there's also a channel for this specific tutorial at the moment, which is T20-fri-geo. So if you do go and join as a result of this, and it's, now while this is going live, you should be able to join the channel. I'll keep an eye on it. I am slightly I'm slightly behind on the feed. There's a little bit of delay on it. So if I'm saying something now, it's, 30 seconds or whatever until you hear it. But I will keep an eye on the channel if there are questions that people have about things. So just as a bit of further introduction, so what I want to do is, there's 5 notebooks that I've prepared. The first one I'm probably going to go through relatively quickly, unless I get an indication that I should spend a bit more time, and that is just cleaning some data. If you know pandas, then there's nothing really new here, except that it happens to be a shapefile that we're going to be cleaning and that we're going to save out, and we can then do something useful with in something else. But if you are comfortable with pandas, this is pretty straightforward. Then we'll cover input output and some basic plots in GeoPandas. Then we'll look at how we can process some of these, selecting data by places and whatever. Depending on how time goes, I think we'll probably be able to do it, but we'll then look at joins and spatial joins. So this is if you've got 2 different data sets, and you're wanting to try and combine them in some way. We'll look at a couple of 2 different ways of doing that. And finally, we'll do some base maps, so you can just, make nicer looking maps. We're going to be covering predominantly vector data. So we're going to be looking at points, we're going to be looking at lines, we're going to be looking at polygons. We'll look at how to clean data in a shapefile. We'll do some reading and writing to various spatial formats, and GeoPandas is pretty good about it, the variety that it can do. Creating some geodata frames, whether or not you're starting from importing, or if you've got, a column of some sort of geometry that you can use. And then we'll do some plotting on maps. Map classifier is a very nice thing that can run in the background, and you can bin, for example, point data in a couple of different ways. And we'll also have a quick look at doing some time series stuff that's fairly standard pandas again. And we can't talk about geodata without some sort of projection and coordinate systems being mentioned at least. And then we'll do some data buffering, so we can select within a certain area or whatever. And we can also then look at how to select by spatial relationships. So, okay, we're interested in all of the things within this polygon. And we'll do some measuring of distances. And as I say, then we'll do some joining data both on attributes and on spatial relationships. Explicitly not covered in this is any in-depth treatment of raster data. If you're interested in that, there's been two fantastic tutorials. One by Leo Ueda about gridding scatter data in Verde, And there was one that I have yet to watch, but was apparently fantastic last night from Joe Kington about, just doing all sorts of weird and wonderful things in Python regarding image processing and similar things like that. To be also quite clear, there are other spatial Python things that you could use. So you've got, for example, I think it's called ArcPy. Yeah, ArcPy and PyQGIS. They interface with ArcGIS and QGIS respectively. If you're wanting to do stuff, if you're wanting to automate processes within one of those, I've decided not to carry on with, or not to focus on either of those, because I don't know what people have available, and I'd rather just keep this as something that is fairly easy to approach. But definitely, if you're using a GIS system regularly and you're wanting to start scripting, at least some of the stuff is going to cross over. You've got the same sort of processing powers available. And I'm also not going to be doing anything interactive. There are ways of doing this. You can export things out into Leaflet, which is a JavaScript library for doing interactive maps. You can also do stuff with Folium, which is a Python version of Leaflet. So we're not going to be covering that. If you have been able to do it, we've got the easiest is a local setup, and that's what I'm going to run. But there is also a binder version of this repository. So if you click on here, you should be able to run everything as expected. If you're having problems, I know that there was somebody who had some trouble with GDAL when running things. So if you have problems, fall back onto this. I think that there is a limit on how many people can use it simultaneously. So if you've got your own environment, you should use that. So what we've got, sorry, this was me testing earlier. So if you've not used it, I can't make this bigger, I'm afraid, but we're going to activate the T20, mine says Wednesday, yours will say Friday, environment, and then we're going to start a notebook server. If anybody needs me to go over this, please do say so, but I think most of the tutorials so far have done that, so hopefully you're all comfortable with that. And with that, I think we can dive in and take a look. If we go to the notebooks folder, we will start with this one. If people indicate in the Slack channel that this is something that they don't really need yet, then I'll skip through it a bit faster. Otherwise, we can spend a bit more time. So as I said, a lot of this is going to be pretty much standard data cleaning. You don't need Geopandas to do most of what's going to happen in here, except that what we're importing is a shapefile. So we're going to import a shapefile, and we're going to look at it, and we're going to get an idea of what it looks like, and if there's anything useful in there, or what do we need to change to make it something we can take further in our processing chain. So we will import Geopandas, Pandas, and NumPy. Geopandas is essentially a wrapper for pandas, so all of the usual data frame methods are going to work. We just get now some spatial awareness about them. So what we want to do first is we're going to load up some data. And if we have a look, you can see that there is, or if you have a look in the folder, you'll see that there is a data folder. And by using tab, we can get some autocomplete. You'll notice that shapefiles have a whole bunch of different things. We want to load the .shp if you're loading a shapefile. So we're going to do that. And the standard way of doing this is with geopandas.read file. So where pandas has a whole bunch of different read files, so you've got read CSV, read Excel, a few others. Pandas just does read file, and it will figure out what you're trying to do. So we can have a look at what this data actually looks like by just printing it out. Let's actually do it as a head. So we can just look at the first few. we can see that we have, this looks like a fairly standard data frame. What makes it a geodata frame is the fact that it has this geometry column and that we can do stuff with this geometry column. In terms of cleaning stuff, the company is possibly going to be one that we want to have a look at. So if we're wanting to have a look at just the company, we can do that using the standard thing here, where we're going. This is, as I say, helps if I can type. And now we can see that we've got a long list here. So we've got our 207 object or 207 rows in our data, and we've at least got, Mobil, Shell, ExxonMobil, Encana, Marauder, Encana that are present in the data set. An easy way to get an idea of what's all in there is to use set. So if you give a set a list-like object, it takes only it only gives you the unique ones. So we can have a look here. And if you have a look at this, you can see that there's some messiness to it. So for example, all of this pan-Canadian stuff, that's probably all the same company. So we can collapse all of these into one. You can see that, do we need to really worry about what the difference between the 4 different Mobil oils are here? That may well be something that you do care about, but for our purposes and for illustration, we're going to consolidate them. The easiest way to do this for text strings in pandas is if you write some regex. Now, regex can be quite complicated, but in this case, I've commented them as well to explain what it does. And we're going to create a dictionary where the key for our dictionary is what the regex is going to be, and then the opposite side is what we're going to replace it with. So our key is, it's going to look for our key in the strings, and then it's going to replace it with whatever the value of that key is. So for the most part, these are fairly straightforward. When I went through the list, I saw, for example, that there were a few typos. So petocan should be petrocan. Doing some fixing to make sure that the capitalization is consistent, things like that. If you're interested, have a look through. Most of these are fairly straightforward. And what we want to do now is we're going to create a new column. And this new column is something that we can use to create the actual data. So we're going to replace it in place. So we're going to change the original data frame. But we're going to keep it as in a new column, just in case we need the exact company that was entered for some reason. So we're going to take our well data and we're going to assign it to owner. And we want the well data of the company. And the function we're going to be calling is replace. And we're going to replace it with a regex. And our regex is going to be this dictionary that we created in the cell just above. And if we also then straight away say we want to see what our well data owner looks like. Where did I go wrong here? Typo, sorry. The hazards of live coding. So you can see that we have now a much more reasonable list of combined ownership. And this, if we're wanting to, plot a map with all the owners, this is going to be much nicer than trying to deal with the 47 we had above, where we don't know which ones are duplicates and things like that. So I think we have a little time. I'm not going to spend too long on this, but especially if you're following this later, do try and pause and have a look at what we're wanting to do here. There's exercises scattered throughout all of these notebooks, I think, except for the last one, where the exercise is, essentially identical. But what we want to do is we want to have a look at what else we might need to clean. And again, if you're not comfortable with regexes, then you don't have to stress too much about trying to keep this. This is just, if you're watching this in the future, it's a good exercise to try and do this stuff yourself as well. So you can see here that what we want is we want a list of the unique values in the well type series, because that seems to be, when we looked at that, there were a bunch of different variety, or the well type could be varied. So, and it seems likely that that's something that we're going to want to plot at some point in the future. So I'm not really going to wait in this notebook, but I may wait in some of the others. So we can get our set of well data, and we want to have a look at the well type. And you can see again that we've got some broad things here. We've got a delineation, wells, development wells, development and exploratory, exploration, delineation, exploration, del, sidetrack, exploratory, and service relief. Again, we're going to combine these. So there's a clear typo in this development. We're going to want to change that one. So again, setting up a regex. We don't have to set up a regular expression to do this. If it's a simple case of, it's just a text string that's gone wrong, you can just use the text string like that. This is going to change a new line and a character. So it's the new line and the ampersand will be changed to an empty string. This will take any excess white space. So if we've got white space, more than one space, it gets changed to a single space. And then the other one that we want to do is we're just going to combine all of the exploration stuff into some sort of exploratory. So exploratory, and we're going to change that. Sorry, that's what we want to change it to, exploratory. And we're going to change the exploration. Sorry, we want to do it exploratory. And we're going to change exploratory to exploration. That's the way we want to do it. And again, we're going to change it in place. So this is going to overwrite the column that we originally had, because there's no real value to keeping these ones where there's clear typo or something incorrect. And you can see when we print it out now, we've got the same features, but if we print that as a set, if we do this as now a set of our well data, and we want to look at our well type, you can see that that's a little bit cleaner. Wait a second, something wrong there, because that hasn't updated. Sorry, give me a second here. We can also, maybe I misunderstood where the, okay. Oh, that's a typo from me. I spelled it correctly. Development. That explains it. Okay, so, okay, sorry about that. Okay, so in some cases, the column names are not particularly helpful. We can see that we have a variety of different column names. These are easy to get using our standard pandas, where we can just get the columns. Something to be aware of if you're going to do this with shapefiles is that the maximum length of a field name in a shapefile is only 10 characters. It's just a limitation of the format. So if you have to use shapefiles, you need to make sure that you're keeping less than that. You've got field names, column names less than that. Other formats, G packages, for example, they don't have that limitation, so you can have much longer field names. And that's one of the reasons why you've got a bunch of weird things in here. So you've got wellnam_1, well name, water depth, total depth. And I want to emphasize as well that this is real data from the Canadian, these are offshore of Nova Scotia, and this is what we sometimes end up dealing with. So, we can make some changes to this, and the rename function in pandas is what we can use. So at this time, at the moment, we can just give it a dict again. So we can say that we want our series names. What we want there is we're going to change these, and we're going to change well termi to well end. That's the termination date of the well. And we're going to change well nam1. We're going to change this to a well code. And this is just based on looking at what they were earlier. And then we can just use our usual pandas function here. We can rename, and we're going to rename the columns based on series names. So something to be aware of here is that we've changed them here. So you can see that we've now got a well code instead of well nam1, but this hasn't changed our original data. So if we have a look here, you can see that it gets kept as well nam1. And this is because we haven't used the in place option. So what we can do if we want the actual, if we want to, we either need to do something like well data, and we want where we can do well data equal, oh no, that will overwrite, sorry. We can make, it returns a copy of the data frame, so we can overwrite the original. So well data equals well data dot rename, etc. But the slightly cleaner way is if we say that we want to change it in place. And you'll see that now this gets us what we wanted. We've now changed the well code here. And if you have a look, you can see we've got well end instead of well termi. So yeah, a lot of this exercise is going to be more or less the same. I'm not going to write all of this out. I'm going to copy some of the stuff over from the other side. We can see, for example, that we've got, if we're looking at the different stuff that we have here, our well data, we can quite easily get whatever we're wanting. So these are our different types of wells. We could use these. These might be useful. This one, if you have a look at drilling U, it becomes quite clear. If you have a quick look, you can figure out what this is, but definitely the name is not very useful. So if we look at the set, this is clearly some sort of drill ship or rig that's been used to create these. So one of the things that we'll change is just to make that a little bit more readable or a little bit more understandable. So let's see, we should be able to copy that in. So we'll change drilling U to drill ship, and we'll clean up some of these other things as well. And as I say, remember that something that we need to do if we're going to keep this as a shapefile is we need to check that these aren't longer than 10 characters. Otherwise, you can change them here, but it won't let you save it as a shapefile, and you'd have to change it at the end. So this is just a simple way to check if a particular series is longer. And, if they're not longer, then what we'll do is we will change it. Actually, the logic on this is somewhat flawed. We should do this in a different way. Sorry. So what we'll do is we can check if anything's longer. We got nothing back, so none of them are longer, so this will work. We can save it as a shapefile. So we've now changed those. We've now got our drill ship. We've got water depth. These are just slightly easier to read if we're wanting to take them further. So we now have a hopefully improved data frame that we can use. I'm not going to really go over this because we can't save date times in a shapefile. So I'm going to skip over this for now. If you need to do datetime or time series analysis, you can import a shapefile, convert the string that has your current date and time into a date time that you can then work with normally. Otherwise, what we need, and then you'd need to change them back afterwards into a string using something like string format. Otherwise, there are other packages that can handle a date time being written to it. Shapefile is a fairly old format. It's nice and stable for the most part, but it's got some annoyances. And these exercises are probably quite worth doing. You can figure out your time difference, how long were various wells operating, and things like that fairly easily. And you could then have a look at where a well was the biggest, or where a well was operating for the longest. Obviously, we need to be able to save these. Geopandas uses a package called Fiona in the background, which I believe is an interface to GDAL. But in any case, normally you don't need to import Fiona directly, but because we want to have a look at what the supported drivers are, we need to do that. So Geopandas out the box is going to read all of these formats. It can also append and write to shapefiles. It can append and write to BNAs. It can read and write geopackages. It can't append to those. It can read topo.json and a few other things. So certainly most formats that are common will work with this. If you've got something highly unusual, you might need to figure out another way. But there are you can do some stuff here. Sorry, I notice. Yeah, Jan, I think that definitely using these regex replacements, if you've got fairly consistent data, it would work. It might take a bit of effort to get the right matches to match everything. The way that I would suggest you do it is you do it incrementally, and you have a look and say, okay, well, this is the sort of shape or this is roughly the string that I want. And even if you've got a lot of different ones, it might take longer to run, but make those small little changes. So you'll notice that one of the things that I did is I stripped off the white space, and then I changed the capitalization, and then I did the other thing, the next step. So I think the way to do it is to build up, and don't try and match everything with one complicated regex. Regexes can become very difficult to read and understand what they're doing. If you keep it simple and you just say, okay, well, all I'm doing is stripping the white space, all I'm doing is correcting the capitalization, you can have a long string, and the stuff will cascade through. So it'll start with the first one and then go through. And Chris, this one I'm going a little bit faster through because I'm expecting people to know a little bit more. Once we get to working with the actual Geopandas interface and everything, I will slow down. And there is a complete version of the notebook in the master folder here. So if we go back here, if you look in here, there's a completed version. I'd suggest, if you can, to follow along in the notebooks version, but the completed one is there. And as I say, I apologize for running a little bit fast through this one. If this is more useful, I can slow down a little bit more. But as I say, I think the idea here, or my idea here, was just to show you that you can load a shapefile and then do all the usual stuff that pandas can do. So none of this is GeoPandas specific, except that we're loading and saving a spatial file. If this was loading up a CSV, all of these things work. And you don't have to have the cleaned data to carry on. I've got a clean version that we're going to import. So if you've fallen behind on cleaning stuff, or if you've cleaned it in a different way, or you've had an error or something, we're going to load a version that I've cleaned. So we should all be starting with the same data. So we're going to save a geo package. These are quite nice. It's not really relevant here, but it's a SQLite database in the background. And what that means is that you can have multiple layers in a single file, and there's a couple nice features that it has there, which you can work through. So this is as simple as giving your initial file name. And with our file name, we're going to save it to data, and we'll keep the same, we'll keep this, but we're going to say that we want it as a geo package. And I'm just going to make it explicit and easier to find that this is a geo package of our offshore well. And if we're wanting to save this, then it is simply a write. We just use the to file option. So well data, and we're going to go to file, and we're going to give it an F name, and we will give it a driver. And the driver names are these strings in this dictionary here. So if we want to save it as a geo package, that's our string there. I believe they're not case sensitive, but I'm not sure. So we can check that actually, so we can see if it works with a lowercase. No, so they probably have to be uppercase. What did I do wrong here? So, okay, can't save it as a geo package, or can't have the first part of the name be geo package. It's a reserved layer. You can explicitly say that you want a layer for geo package. The geo package driver, we can say that we want a layer here, and we can say that this is going to be, our well data if you've got multiple things here. And then what we can do is, you can take this and load it up in QGIS or ArcGIS or whatever. If you do the stuff with the date time that we skipped over, the date time here, we can't, Esri shapefile doesn't support date time fields. So we're not going to, so we would then need to convert our date time back to a string. The easiest way to do that is by using the string format. So if you do something like this, we can get the date time, so we can get the date, and then using it as a date time object, we can then do a string format to change the time. This again is in the pandas documentation rather than the Geopandas documentation. And something else to just be aware of is that if you're wanting to, if you need for some reason to change the projection of your data, we can do that fairly easily as well. So if we want to use a more local one, so this is a UTM projection, that's what we imported and that's what we saved at. I haven't covered that yet, but we can quite easily, if we're going to save it to somewhere new, we can give it, and instead of UTM, we can change this to a geographic. We can change this to something geographic, where we want, lat long degrees rather. And that's as simple as when we save it here, we can use it to CRS to reproject. I'll go back over this just now, but this is just a quick example here where this is going to save it. It returns a copy, and we can obviously now string our things together, and we can then to file. I'm going to save it as our F name. And what we can do here is it defaults to a shape file, but we can explicitly give it the driver that we want, S3 shape file. And if we have a look now in our data folder, you can see that we've now got a geo package here that we created. We have also now got an additional geographic shapefile that we've created. So this has now been reprojected. And if we load this there, and we'll look at that in the next notebook, you'll see that this all looks a little bit different. There's a big difference between the two. So this geographic is using a latitude and longitude, and this is using a projected coordinate system in meters. So, okay, that was a bit of a whistle-stop tour through the first notebook. As I say, it's more focused on just showing that you can import and export a shapefile and clean that up and do stuff with it. I'm going to move over. I think I've only been going for a short time, so what I'll do is I'm going to move into the next one. If people need a break or want a break, speak up in the Slack channel. I think there are a few natural breakpoints in this. Otherwise, we'll take a short break at the end of this second notebook, where we're going to deal with I/O and some basic plots from Geopandas. Okay, so if we're wanting to deal with stuff, not everything is simply numbers and letters, and especially for geosciences, a lot of it has got some sort of location data associated. We've got a variety of different data formats or that we can think about, and one way to think about it in terms of dealing with things spatially is whether we're dealing with raster data or point or vector data. So vector data, we've got points, lines, polygons, things like that. Raster data, we have essentially images or height maps or similar things like that. As I mentioned, check out the stuff from Leo and Joe. They're really good tutorials. I'm looking forward to seeing Joe's one a bit later, but that's well worthwhile. And if you want to deal with that. So we get some things for free by using Geopandas, and free in the sense there are some common operations that are easily done in here. And if you're trying to set up an automated workflow, this may be something to consider instead of doing it in ArcGIS or QGIS. You can automate the stuff in there as well. But if we're wanting to do some sort of, if you're wanting to set something up that you can just call a script, this is a very nice one. It doesn't rely on having QGIS or ArcGIS installed. And you can get quite a long way with Geopandas. So one of the most common file formats are shapefiles. And shapefiles are interesting because they're a relatively old format, and there's a whole bunch of different files that are associated with a single shapefile. There's a brief rundown here. We have to have a .shape, we have to have a .shx, and we have to have a .dbx. Okay, and the shape is the actual feature geometry. The shx is an index that allows us to access things quickly, and then the dbx is the actual attributes, which are stored in columns for each feature. So this is, if you think back to the previous notebook, this is where you're going to have your column with your drill ship and your depth and everything else, and that geometry column lives in the shape and is accessed quickly using the shape index. Additional files that are often present, there are a few, but the most common that I've seen is a .prj, and this is information about the projection that the data has. There are also spatial indexes, which are either SBX or SBN. These allow you to identify place quite quickly, which is just easier. And there's a metadata file that you sometimes come across, which is a .shape.xml. These are common in desktop systems, but they're a little bit clunky if you're trying to pass things around on the internet. It's very common for people to, for example, when you say, please send me the shape file, they only send you this. So there are some drawbacks to the format. There are also some size limitations on it. And as I say, the fact that you can only have 10 character headers can be frustrating. If you're trying to do stuff in a more modern way, it's often easier to put things on a database somewhere, or if you're passing things around on the net or over the internet, GeoJSON is actually a fairly popular format. It's got its own issues, but in any case, that's just historically shapefiles are the most common and are the most important. I'm also going to, so just to add, I'm going to make an effort to talk a bit slower. I tend to talk quickly at the best of times. So if this is if this is slow and you're watching in the future, speed me up, but I'm going to try and slow down. I apologize for that. So Pandas gives us a data structure called a data frame. And that's really nice in terms of dealing with rows and columns. And Geopandas is an expansion on the data frame. And the way that it does that is by adding a geometry column. It also adds some additional methods, but that are focused on dealing with spatial relations between things. But you still get all your initial data, all your usual data frame methods still work. So anything that you normally do in Pandas, if you've got a geodata frame, should all work. We're not going to go too into the weeds with it, but if you have a library that takes in data and you're then wanting to now suddenly start putting additional stuff, if you now want to start putting additional spatial awareness on, it's not quite drag and drop, but you can quite easily adapt it to use a data frame, geodata frames instead of data frames if you're already working with those. So what we want to import here is our usual suspects, Geopandas, NumPy, and Pandas. Map classifier is an optional one, and we actually don't need to import it directly. I just want to highlight that that we're going to use it. It allows for easy binning of data. So you can, if you're wanting to find natural breaks in your data and you've got a long list of numbers that you want to bin, map classifier is quite a nice way of doing it. And Geopandas, when we're plotting, can go straight through to map classifier and allow us to work with that. Initially, I was importing CartoPy, but Pandas can actually handle the CRS stuff directly on its own, so we don't need that. As we saw, loading a data file is pretty straightforward. We say where we want it, we read the file, and now we load it. This should all look familiar. This is a geographic version of what we cleaned up in the last notebook. You can see that we've got our geometry, and you can see minus 59.91, etc., 43, that these are in geographic location, that these are in latitude and longitude. We've got some other things here. Now, this is fine if you've got an existing shapefile or geopackage or anything that Geopandas can read. But often we get data that isn't actually that doesn't have an existing geometry that's built into the file. So we can load a CSV, for example, and as long as we have something to relate the location of each row, we can create a geodata frame. So I'm going to load, this is from the International Peace Information Service. It's artisanal mines in Zimbabwe, and they went and looked at issues that people may have there. And you can see that we've got these 42 columns. There is a geom column, okay, and we can use this, but it's not the actual geometry column, because if we try and plot if we try and plot this using our usual thing here, and we've imported this as artisanal mines, you can see if we plot this, we get a fairly standard plot that we would expect. It plots all our numerical data. We would like to actually plot where these data are. So since we have the geom column here, if we take a look, we can see that these are something called a well-known text string. And these describe geometries. There's a Wikipedia link here if you're curious about it. But essentially what this is it gives us a nice unambiguous way to describe geometries using a simple text string. And these are fairly easy to understand, fairly easy to read and write. That's taking a while to load. I'll let it load in the background. And what we want to do is, if we've got different things, you can see that we can represent points, we can represent lines as a list of points, we can do polygons as something like that, and we can have then things inside. This is something that we can convert to something that we can use. The easiest way is by using Shapely. So Shapely is a direct, or the Shapely library can handle WKT. If you have something other than WKT, Shapely can probably handle it. You just need to know what your columns are. So you may have a column which has your latitude and another one that has your longitude, for example. This is especially common with point data, and it's especially easy in CSVs to do something like that, where you have a column which has all your latitudes and a column with all your longitudes, and to convert that to an actual geometry that you can use for Geopandas, we need to then link those together into a geom that Geopandas understands. So what we'll do here is we're going to use Shapely. The apply function is one that works in pandas as well, and it does a particular operation to every row in the data frame. So what we want to do is we're essentially going to load a WKT, or we're going to use the WKT.loads method. And again, if we're curious about what these are, we can, let's just do it above here, so we can take, because of the introspection in Python generally, we can do this sort of thing where we can now have a look and we can see, okay, well, what are our what methods do we have available to us? So we can dumps, loads. And if we have a look at what loads does with Shift Tab, you can see that this loads a geometry from a WKT string, which is exactly what we want to be able to do. So we're going to, for each string that we read in, we're going to load it, and we're going to save it as a geom here. And I mean, this looks almost identical. So except that the actual data frame has now loaded this in. We haven't given this a CRS yet. We don't have to. A lot of the stuff will work relative, but if we're wanting to actually put this in position on the Earth's surface, or if we've got a different data frame that has got a CRS and we want to be able to link the stuff together, we should we should tell it what it is. With just plain decimal degrees of long and lat, using the WGS84 is a good option. And you can just set that variable. So the CRS variable here is just a property. It's a coordinate reference system. Let's just pop this out. So this is a CRS represented as a pyproj.crs object, returns none if it's not set, and we can set the value that we want. It's anything that can be accepted from this. So it can be a WKT string, it can be an authority string. The authority strings are usually fairly reliable. So what we've now done is we've now told it that when you see a particular point, this is how to relate it to the surface of the Earth. So what we can do now, and you'll notice that when I did this over here, I saved it to a new geodata frame. So just to refresh our memories, if we plot normally, this is what we get. We now have, but we now have a geodata frame that has a CRS and that has that geometry column. It knows what the geometry it needs is. So when we plot it, we now get points in space. So we can do this directly if we don't have to create this geometry column. So if you're loading a shapefile, you can load the shapefile and immediately just say plot. But we've got a few extra hurdles that we need to jump through if we don't have that convenience. But you can see that we've got a bunch of artisanal mines, and there's no context or anything, but we can get locations, and you can see that this is at 20 to minus 20 to minus 20 and a half degrees. So this is fairly limited in space, but it's there. So the geodata frame that we have is actually plotting our coordinates. And the standard frame is just using the index, and anything numerical gets plotted. So yeah, I'm going to take a short pause here. Have a look at seeing if you can find in the well data, and remember that well data we've got these well locations. So if you're fairly comfortable with pandas, give these a go. I'll give a minute or two to wait until I see somebody pick something up in the Slack channel maybe. So give it a try. See if you can tell me what the deepest well is, and see as well if you can tell us how many were operated by Canadian Superior in particular. If you have a look, there's a short hint here that sort values by column may be useful, or sort values in a particular column. And if there's any comments or anything about creating these geodata frames, this is also a good place to put them in the Slack, and I can go back on them, re-explain if I need to. Okay. All right, so hopefully you had a chance to give those a go. Again, these are fairly normal pandas operations. So I'm going to show you a way of doing it. There are undoubtedly others, but these are ways that I'm familiar with and that I feel are the easiest. So we can sort values in a particular column using pandas. So we're going to do it on the depth in meters, and we're only interested in the last value, so we'll just use the tail. Sorry, it gives us the last 5. We just want the last one. So the deepest one was nicely drilled by a drill ship Deepwater, and it is well named Crimson F81. And yeah, you can see that it was an exploration hole and it's a plugged gas show. Sorry, hang on. And if we're wanting to see how many were operated, we can build this up. So what we want is, we know that we've got the well locations and we know that we have that owner field. Okay, and what we want is, we want where that owner is Canadian Superior. Okay, and we're going to want to use this as a selection, so we can do that with this shortcut here. Okay, this gives us the whole lot back. So you can see that gives us the 3. 3 is fine, we can immediately see what that is, but if we had more, then we may want to wrap that in a length function, which gives us back 3. If we change this to something that has, to one of the companies that have a few more, so for example, if we change that to Shell, you can see Shell is operating 54 wells in this area. All right, so we can also have a look at where these wells are. As I say, I'm going to stay with the well data. It's a little bit more actual geoscience than the artisanal mines. The artisanal mines are a social and conflict data set rather than a strict geoscience one. So I'm going to focus on something that I think more people have a bit of understanding on. As I showed, we can just use the dot plot method, and you can see that this is plotting with our latitude and longitude. We haven't done any differentiation. If you don't know off the top of your head that minus 61 west, 45 north is off the coast of Nova Scotia somewhere, that means very little. I just want to show you as well, and this is going to be important for if we've got data from different sources. Sometimes they can be in different projections. So you'll notice that here I'm loading a UTM-20 NAD83 shapefile. And this is notice that this is a clean one. So if you haven't done the notebook 1, you can jump straight in with this one. There is a clean data set. And this is fairly straightforward and similar to what we've seen. We've got the F name, and we're going to read that file in. I'm doing a little bit of additional cleaning because I'm reading a shapefile in. I want date times for the start date and the end date for the wells. So I'm changing these 2 date times. So I'm just changing them in place. And just in case, I'm going to replace any instances of none with an actual nan. And then we can plot those, and we can have a look at the first few columns. So this all looks very similar, but if we have a look over in our geometry, you can see that these are very different numbers. We had 41, minus 41 and minus 61, 45-ish. now we've got, a few tens of thousands. So when we look at the plot here, you can see that these are not going to plot anywhere near each other, even though they're exactly the same data set. And this is because they're using a different coordinate reference system. So that's quite easy to find. You can just, call the dataframe.crs method as we used it earlier to set data. Now we can just get the stuff back. And you can see that the wells, the one is in 4267 and the other is in EPSG code 26920. Now, if you know what you want, that's fine. If you don't know what these are, EPSG.io and spatialreference.org are a really good place to find what your data might be. A lot of this is going to depend on the sort of data you get and how big the data, how wide the area it covers is. The obvious one here is that if we've now got our data frame and we've got a CRS, what we can do is we can actually plot the data on top of each other. Or we can now, if we get the same CRS, we can now combine the two together. So what we can do is we can and we can also then reproject our data so that they are in the same data set. So what I'm going to do is I'm going to take our UTM data and I'm going to reproject it. I'm just saving it with a new variable. And with our well locations, UTM, we just use .2CRS. And I used this very sort of almost in passing at the end of the last notebook. The easiest way that I've found is to give this an EPSG code. You can do other things, but this is the simplest that I've found. And if we change it to 4326, should actually make it the same. There are some minor differences between 4326 and 4267. So we can reproject this data. And then what we can do is we can create a plot because we want to be able to plot these together. I'm going to save it to an Ax object. You can see that this is built on top, or this is built on top of Matplotlib for the plotting library. So a lot of the stuff that you use there, you can use here, creating figures and axes and things like that. And then we'll take our well locations, which remember are in latitude and longitude, and we can now plot these as well. And we can pass an Ax object, or we can tell it which Ax we want to use. And just to highlight that these are different, we're going to do them in a different size and slightly transparent perhaps. So all of these keywords are standard Matplotlib. And if we plot these, they should be on top of each other. And you can see that we now have that. So if you've got two data frames or two data sets, one in one projection, one in another, if you know what they are and you know what you're wanting to end up with, you can put them together. Okay. There's a question on the advantage of PD to date time over as type. I'm not sure of the minutiae of the advantages, Malcolm. The PD.datetime to date time is a built-in, which I think may be a little bit easier. I'm not sure if there's a speed difference or if there's a minor difference in implementation. I know that Pandas does have its own implementation of date time, where it creates a timestamp object or something. But that seems to be really down in the weeds in terms of what the actual differences are. So it's possible that as type might be better, but I'm more familiar with to date time, especially when making date time indices and things like that. I'll have to try that though. Okay. So carrying on here, we've got these points, but just plotting them on their own doesn't tell us very much. Okay, we want to know, for example, who's operating which well, how deep is each well, all of this sort of thing. So we're going to go with total depth to start with, and we can give it some style. So what we can do is, and I'm going to do it with the UTM data. Again, you can use, remember you've got all your tab completes and things which are worth using. If we give it a particular column, okay, and in this case our column is going to be depth M for depth in meters, it's going to color or it's going to classify and plot the things in that color or using that column's values. Okay. We can also pass it something called a scheme. So if we want, for example, percentiles, okay, and I'm going to give it a K of 6. I'll explain this in a second. And we will then display a legend. And we can also just, are these plotting large enough? I'm going to just give it a fig size to make it a little bit bigger. Or hopefully a little bit bigger. Okay, so this scheme is something that gets passed to map classify in the background. It basically bins the columns. If you pass something that it doesn't know, then it will give you an error that explains what all your options are. But you can see here, let's actually make that slightly bigger. So you can see that instead of having to rely on a single color bar that runs, up the side or whatever, we've actually binned our data into something that might be useful. So, you can now see that anything that's yellow is between 6,472.5 meters to 6,676. You can see maybe that there's some trends in the depth of our wells. We've got some shallow ones over here. Our deeper ones seem to be in this big cluster down towards the bottom. We can change this to, for example, we can use a standard and mean. And the K is how many classes we want of a particular thing. Let's just copy this instead. So C and V in a notebook, by the way, copies and pastes a cell. So what we can do here is we can, for example, plot the standard and the mean. I think in this case it will ignore the K anyway, but you can now see that we have the breaks according to where our standard is and our mean. We can do other things. There are other ones available here, so we can do, for example, quartiles. Missing you. No, sorry, I got that one wrong. In these error message, you can see these are all the options that we have available. I was looking for quantiles, not quartiles. So this is actually quite a help. You get quite a helpful error message. So here again, you can see these are now quantiles, which is essentially an equal count. So it tries to put the same number into each bin. And this is very nice if you're dealing with this sort of point data where we want to be able to say, okay, this is where we've got particular things. And you can see that in this particular output, we've got we've got deeper wells in this area, and they get shallower as we head up this way and out this way. This only makes sense for some data. So, if you're trying to plot the well type, for example, it's not a continuous numerical stream. We can still pass it as a column. So if we plot this, again, we're going to give it a column, and in this case, we'll go with the well type. And remember that we saw that the well type is a text string. The legend will be useful. And yeah, we can change our color map. All our standard color maps are available. And I will make the figure size again. And you can see that now what we've got is this map is now being colored according to the type of the well. And you can see that there were a few development wells here in the center, wide spray of exploration wells. There's probably one or two of each of the other types buried in this little cluster in the middle. There's quite a lot of stuff going on there, but maybe we're interested in what's going on there. So one of the things that Geopandas adds is a CX method. Okay. And if we look at the CX method, we can extract areas that we want, that we are interested in. So we're only interested in that main field in the section in the center. So we'll take our well locations and we're essentially going to slice the data here. So looking at it, we can see that we're, call it 65,000 or so to 80,000 on our x-axis. So our longitude, so 65,000 to 80,000. Okay, and if we've got that, these numbers I've pulled already from experimenting a little, but a little bit more than 48,000 here and a bit more than 49,000 there. So we can go with that. 1,002. 0. Okay, and what we can do if we have a look now is if we print the shape of our main field, if we take our main field now and we look at its shape, you can see that this no longer has those 207 wells. We've restricted it to only the 145, and those are the 145 that are in that particular section, that fall within these coordinates. So if we plot this now, and we can use, maybe we'll plot them by owner in this case. So this works exactly the same. It is just a data frame. So we'll plot them by owner, and we'll want a legend, because otherwise we won't know who's whom. Assuming I can type at some point. And in this case, I'm using a different color map because we're going to end up with a bunch of things that we want to differentiate. And we'll use the same fig size that we had let's make it a little bit bigger, 7 by 7. And what you can see now is that we've zoomed in on that cluster in the middle, and we've colored it by the various owners that we had. And you can see, for example, that shell or that mobile is sitting with this brown across the middle. We've got, shell sitting on either side. Yeah, so we've now got a little bit more insight into the data. We've been going for a while now. We're nearly done, and I think at the end of this notebook, what we'll do is we can take a break. But in the meantime, here is an exercise to work with. You can see if we're using the datetime columns from earlier, we can now do some stuff to figure out which well was operating for the longest, and we can actually get an idea of how long that was. We could also, once we have that, we can do stuff like figure out which is just get a frequency analysis of which wells were open or which wells were operating for the longest. And we can have a look if there are areas of the well or areas of this field that had longer operations than another. This is a slightly contrived example. We would probably have this information from somewhere else already. But if you're wanting to give yourself a bit of a stretch over the break, if you come back a little bit early, give this a go. I will come back to this just after we finish, but I'm going to talk about just saving stuff again, just to show that we don't really need to worry too much about what we're saving these things as, or, that it's quite easy to save things. So if you want, for example, a GeoJSON file, we just tell it that we want a GeoJSON file. So we can, and this is, again, not something that's too difficult to do. And GeoJSON files, for those who aren't aware, are just JSON files that have a geometry associated with them. So we're going to save this as GeoJSON. It's already there. I think I ran through this a while back, so it exists. And we're going to take our well locations.utm. Something to be aware of for GeoJSON is that it only accepts the WGS84 datum, so we need to reproject this first. And the WGS84 datum is this 4326 EPSG code, and then we'll save that to file. Okay, the fname, and in this case we need to give it the driver explicitly, that this is going to be a GeoJSON. Something to notice is that GeoJSON is fine with getting datetime files. Okay, earlier on, or if you try and save this, if you try and save one of these, if you try and save this UTM one where we changed it where we changed the date times, it's not going to work. So just as an example, just to show you that we do get that error, if we save it here and we don't give it that, and I'm just going to add dot shape, it gives us a driver support error, and it tells us if we go all the way down, its through shapefile does not support datetime fields. If we wanted to save this, we would need to convert those date times back to normal strings. Okay, so just something to be aware of if you're going to read something and do analysis, especially time series analysis in Python, and then write out a shapefile, is that you're going to have to convert those date times in some way afterwards. That initial function that we had above, this one here, if we want to save it as a GML file, so GML is basically it's a GeoXML file. I don't really know of anybody who's used them, but they're out there, or they can be out there if you want them to be. So we can go with this and we'll do the data. And again, I'm just, and this is going to also be a geographic one. So we'll take that, we'll change it to a GML, and I'm just going to make it easy to find. So we'll have a GML of our offshore, and that saves no problem. And if we come back here and have a look at what we have in our data file, you can see here that we've got these two files were created as a GML. We should be able to open this, and you can see that we've got this XML here. It's got some stuff that it writes in automatically for us, but if you've got something that needs XML, it's there. And where was the GeoJSON one? Sorry, there. And here we've got a GeoJSON file with the same thing. You can see that it's got the important bit that makes it a GeoJSON file, in effect, is this geometry object here. Or everything else would just be a standard JSON file. And it's got some detail on what CRS it is. You can search for that and find that somewhere. With that, I think let's make it 15 minutes, so we will be back at 25 to whatever your next hour is. Give this exercise a go over here. When we come back, I will go over that, and then we will move on to doing some actual processing or some spatial processing. And this is, so far we've done file IO, reading and writing these various spatial formats. We've done a little bit of cleaning quite quickly, but we've done some cleaning on it. We've done some basic plots, and hopefully you're seeing where this might fit into workflows that you have. But yeah, I will see you guys in 15 minutes or so. Thank you for the time so far. Okay, so cool. So hopefully everybody got a chance to replenish tea and do whatever else they needed to do in that short break. Something just to remind people is that if you're having a bit of trouble getting stuff installed, do try the binder version. I don't believe that we have that many people that at the moment that it's oversubscribed. So if you're having trouble, yeah, some people seem to be having random issues with installing Geopandas. We can try and fix those later, but honestly, I've not had those problems, so um, I'm not sure what's going on there. But give the binder version of the repo a go. That does seem to work. I did test it the other day. Okay. So before the break, we were talking about doing a little bit of time series or analysis using some date times on this data frame that we've got, where we want to get an idea of which wells were operating for the longest and stuff like that. So what we can do is if we take our well locations, and we'll work with the UTM data. If we're working with our well locations, we can easily add a new column for how long they've been operating. And what we want is we want these well locations and we want the time. So we want to go from the end of the well, basically, so when they stopped, and we can simply subtract from when they started. Hopefully, so far, so clear. Spud date. Any of the people who do well stuff will have to tell me what a spud actually is, apart from a potato. And what we can then do is we can then say, okay, we only want the well locations that were operating, and using a very similar logic to what we had earlier. We want these where they're operating. We want the maximum. Okay, this will just give us a number. Okay, we want to know what the actual well is. So what we're going to do is we're going to use that as a true or false. We're going to use that to create that we want the well locations where operating. Okay, so where our operating wells are that are equal to the max of the entire lot. So this is simply taking a Boolean across the whole thing. If it's not the maximum, then it's false. If it is the maximum, it's true. Okay, and then what we want to do is we want to use that Boolean where we're only going to show where it's true. So we can see that the well that was operating for the longest was started on the 12th of July, 12th of June 1998. And if we go over to the end date, we can see that it ceased operation on the 30th of June 2001. It was a development well from SOEI, and it was operating for 1,114 days. And it was a gas well. Venture 2032, in fact. Okay, drilled by Roe and Gorilla. All the other information we've got. Because this is, we can pull out all the usual stuff that we have. We can pull out where this is operating. We can convert that. We can access our date time methods using the DT. And what we want is we just want the days that it was. And then we can plot this, and we can plot it as a histogram. Okay. This is a little bit obtuse, but essentially what this is this is pulling out our date time, and then days we can change to months or weeks or years, seconds, if you've got that sort of thing in the data. So if you're interested in this sort of stuff, there's definitely some cool time series stuff or time series analysis that's possible in pandas, and Geopandas can use that as well. And I'm just going to change the number of bins to 30. So you can see if we have a look now, that this venture 2032 well is unusual. It's well above the average. Most of our wells were operating, for maybe up to about 50 days. And then there's a few just over between 600 and 700, I guess. But we've got a very left skewed data set here. So something that we may want to do now is say, okay, well, are these spatially arranged? Is there a specific area that had these longer wells? Okay, so what we can do is, instead of just taking operating, and let me just show you what operating looks like. So if we actually look at what we've got in operating, it has actually saved it as days for us, which is nice. In some cases, it may not always, if you've got particularly unusual, or if your data doesn't, and the reason that it's saved as days actually is because when we created it here, or it's pulling it out as days because it's obviously being clever in the background. But you could, for example, if we wanted this in months, we could now do DT, and we want it in month. Not month. Oh, it's months. Sorry. Not months. Oh, it's because it's a time delta. Sorry. So this is a difference in time rather than the actual dates, rather than the actual date time. If we did this on some of the other stuff, we can pull out the months. So if we pull, for example, our spud date, we should be able to get just the months out of this. Sorry, this is not something I was expecting to have a problem with. I may revisit this and come back to it. Apologies for that. But in any case, yeah, so I haven't done that much time series stuff. This just seemed like a useful one. Apologies for messing up there. So what we can do is we know that we've got these dates. So well locations, we know that we've got the number of days that each was operating, and we can use that as now a cutoff for, if we want particularly long wells. So if we want our long wells, we can take where we've got operating, and this is fairly similar to what we've got. We can use some sort of useful cutoff. And looking at our histogram, it looks like we'll get a reasonable number at around 150-ish. So if we take our wells that were operating for more than 150 days, and this is fairly similar here. And then what we can do is we can create a new axe to use, where we're going to now plot all our well locations. Okay. And we'll just make these gray because, we want to know where they are, but we're not really that interested in exactly what they are, or, we just need their locations. So we'll give it a bit of a size, and we'll just tweak the marker size as well, not to make so that it's not too overwhelming. And then what we'll do is we can now plot our long wells. Okay. And when we plot these, remember that we can pass an axe object to say that it must be drawn on the same axis or on the same axe. Our column that we're interested in is going to be operating. I don't know, we can give it a scheme of, let's make it equal count so that we can get an idea of where things are. And we'll give it a touch of transparency. And we'll want a legend. Okay, so, oops. What have we got? Okay. So in this case, the error that we've got here is that we can't compare date time to an int. So what we can do is we can explicitly pull out the days, because so we should be able to explicitly get our days here. And you can see that these have now been converted to floats. If we don't do this, then we get a time delta. Okay. But we want them explicitly as floats. So what we can do is we can save this as maybe a new column. And yeah, you can see also I've definitely gone over our 10 character limit here with this particular column. So if we were wanting to then take this into a shapefile, we would need to rename this column or do something else with it. So we want operating days here, and we're going to do it with our come on, why do we have another issue here? Universal function, invalid quantiles. I'm just going to see what happens if we do it normally. So you can see that we're plotting that our longer wells were here. I'm not sure why this quantiles scheme has not worked. It should be. It could be another issue where it's a date time rather than an int. Yeah. So we can see here that we've got a relative handful of wells that were operating for a long time, and they're actually, most of them are in this big clump. So we've got some special insights from this. During the break, somebody asked about moving this legend. It is possible. It's a little bit of a faff. What I will do is I'll re-upload these. I'm not sure if I've got it in another notebook somewhere or if it's in one of these notebooks. But what I'll do is I will add a cell or two explaining how to move this outside. This is one of the matplotlib. It's a finicky bit with the matplotlib backend that gets used. So the fact that it's built on matplotlib, and this is how matplotlib does legends, you need to overwrite some of the defaults to force them out. But that's not too, it's not too onerous, but it is less than obvious, let's say. So yeah, I think that, and we've already seen how to save these. Hopefully the random errors aren't throwing people off too much in terms of when I'm doing stuff. So we've now gotten some spatial insights off that data frame, and you know, we might want to be able to do other things where we relate things. So in the previous notebook, what we did is we took a cut of a particular section and said, okay, only show us stuff that's in here. But if what we're wanting to do is, if we've got, for example, areas demarcated as polygons and we want to have stuff in those polygons, we want to be able to go, okay, give me this and only the stuff that is in that. We need to be able to start doing some spatial operations in addition to just slicing our data frame. If your area is irregular, you need to be able to say, okay, I want only this data frame, or I only want data that plots in this polygon or that cuts across it or something like that. So that's what this third notebook, Spatial Operations in Geopandas, is focused on. It's trying to find bits and pieces that are related, but they're not related because they're equal to a certain number or over a threshold. They're related to where they are. I've chosen perhaps a bit of an unusual data set in this case. What I've done is I've downloaded the runways located in South Africa from OpenStreetMap. I've chosen these because I couldn't find a nice fault system or a nice fault system that I wanted to use. So we'll use this. I've taken some code from Bruno Ruas de Pino's post from Geology and Python for plotting rose diagrams. Joe Kington also did a couple I saw yesterday based on image segmentation, but this is just a base thing for getting a rose diagram so we can get an idea of, for example, if the different provinces have runways oriented in different directions. And there's some very nice analogies for if you're working with linear data of some kind in the field. You've got faults in a particular way and you want to see, okay, is the fault regime in this part of in this block different to the fault regime in that block? And we can separate them out without actually knowing, without having a block number as part of the data, but knowing that they are within a given block spatially. So we'll import the usual stuff as well as PyPlot here. I think I'm going to stick with the 7.7 images. So this is just setting a global parameter essentially for matplotlib to use. And as I say, we're going to use the runways from South Africa. I've downloaded and we're also going to load and select the South African provinces from the Natural Earth dataset. Just as a side note, if for some reason you're watching this and you need South African provinces, don't use these. They're at least a decade out of date. There've been some at least a couple of big changes in demarcation. So this is just for illustration. You should get other province data. I can point people to that if they really want it. So none of this is too surprising. We're reading in this case, a geo package with the runways. We're reading in a file. In this case, it's a shape file that's inside a zip folder. And that is actually a fairly nice feature that you can do. So because shape files are a bunch of different files, we said there's at least 3 and probably a few more. If we want to pass them around between each other, it's nice to zip them. And then if you've got them zipped, you need to unzip them. Okay, but if all we're going to do is read them out and use them as a base layer or something, we don't have to rewrite them into the zip. We just keep them in the zip and use it. And here we're just going to select the provinces where the administrative bound or the administrative 0 level of the province is South Africa. Okay. If we look at our runway data, or if we look at our data set now, we can see, for example, so we'll load this ZA runways. Okay. And we can get a feel for what we have in here. So we have an ID, we have an OSM ID, we have a reference, we have what the surface is, we have if the runway is closed, disused, abandoned. We've got a bearing, we've got a length, we've got a bearing in 360 degrees. And you can see that our geometry now is a line string. Previously we had point, but now we've got obviously a start point and an end point. And that's how it's calculated, the bearing. So the bearing is essentially done, I did those myself, the bearing and the length I did, and this bearing 360 I did in QGIS, loaded it up, did some processing in there just to get the bearing and length. We didn't get this immediately. But the length is essentially working the distance between the start and the end point, and similar with the bearing is between the start and the end point. So anyone who's done any sort of structural geology course will be familiar with a rose diagram as a means of visualizing them. It's essentially a circular histogram, and they're common for wind as well. So you've hopefully are familiar with them. And what we're going to do is we're going to use the bins method from NumPy. And this gives us 2 arrays, one with the value in each bin and one with the edge of each bin. And we're going to take 36 bins so that they're about 10 degrees wide each. And we're going to use this bearing 360. Okay. The reason that we want to use the bearing 360 is because if we only use the other bearing, it's going to be between a particular, we're only getting a half thing, but the bearing 360, we might have a runway that was created going from here to here, and then that's got a bearing, roughly northwest. Okay, if we've got another, but if somebody doing the parallel runway started in the top right corner, it's going to have a bearing heading to the southwest instead of northeast. So what we want is we're going to have to copy these across to each other. So you can see I've also got a few things printed out here. I'm going to print out the counts for each and the bin edges, and then we'll see where the first half of the list and the second half of the list. This is really just to show you where the issue is. So this 24 and this 21 are really talking about a very similar bin, and this 33 and this 36 are talking about the same bin, because they should, or not those, but they should be opposite each other. So these should line up when you put them all together. So, and this is all from Bruno's code, where we're going to split our things out. We'll count them together and we'll add the two together so that we've got the half, so that both halves are now equal. Okay. We can now so we've now got a single list where each half is the same. That means that when we put them together, we're now going to be able to count from here and to here, and the points opposite are going to be the same length, which is what we want in this case. If we could reliably know that the direction was all the same, then it would be less of an issue. Okay. And if you were doing something that had inherent direction, if you were doing this with dip directions or something, you obviously then if you've got a dip direction to the northeast is very different to a dip direction to the southeast. But for a runway, it doesn't make a difference, and for faults, it doesn't really make a difference. So when we're making a polar plot, there's some things that we need to have. So we want to have theta, which is the center of each bin. We want the height of each bin, which is the radius out. And we want the width, which is how wide each one is going to be. So what we've got for theta is we want to linearly space out our centers. We're going to take our circle and we're going to step in. We're going to step out so that we've got a nice spacing through there. We're then going to take our two halves that we created up here, which is this here. These are going to be how high each section needs to be. And then we'll get the width that each section needs to subtend, basically. So we'll get the radians of the degrees. And now we'll set up the plot. If you're familiar with matplotlib, this should be fairly familiar. The big difference is that we're using a polar projection. And this is how matplotlib knows that we want a circular plot. And we'll need to set the offset and direction. So what we want from a compass is we want 0 at the top and 90 degrees on the right. And that means that we need to change these from the default, which is to have 0 east and 90 at the top. Okay. And we can then alter the grid that gets drawn on as well. So for all the South African runways, we end up with something like this. I mean, there's maybe some interesting trends where most of them are running roughly east-west. There's very few that run northeast, southwest. Okay. But this is the country as a whole. Okay. Now, if we have reason to suspect that these might be different because, maybe the prevailing winds along the coast in a coastal province are going to be different to the prevailing winds in an inland province, we want to separate these out. Now, if you think back to our runways data frame, we don't have province in there. So we can't easily go, give me the provinces. Okay. We need to do some sort of selection here. So there are a couple different ways to do this. If you're interested, the Shapely docs have a really good example, but the most notable and useful ones for me are, we can check if a feature is completely within another. Okay. We also have if it contains, which is the opposite. So contains will be true if a given geometry is entirely inside a given feature. Okay. Intersects is if you've got interior of two objects overlapping. So, if you've got lines that cross, or you've got part of one polygon is over another one. And then you've also got touches where, you might have one edge of a polygon just touching another one. So these are useful ones. There are a couple of others in addition, but I found these are the most useful. So since I'm in KwaZulu-Natal, let's have a look at the KwaZulu-Natal runways. So what we're doing here is relatively similar. We're going to select, we only want KZN, okay? And then we're going to save a new data frame with our KZN runways. And what we want here is we want the runways within the KZN geometry, okay? So all of these objects, remember that if we're dealing with these geodata frames, what we've got is we can do ZA runways. We've got a geometry column here. And this is giving us all of these line strings that we have. So we can use that and rely on the spatial abilities in the background that Geopandas offers us to now say, okay, give me the runways. Okay, so it'll take the features from this geodata frame, and if they are within a given geometry, this returns true. If they're not, it returns false. So we can use that to select. So we're going to take the KZN geometry from the shapefile of all the provinces. And this unary union is essentially creates one object or one geometry instead of having pieces of geometry. So if you've got, for example, offshore islands and things like that, this may fail. If you take the unary union, it creates one geometry based on all of on sort of sub-geometries within there. Okay. So what we now have is, we should now have in this KZN runways, we should have something that we can say, okay, we now only have runways that are in KwaZulu-Natal. So, we can see that if we print out, for example, the total length of the runways, or if we get the shape of our ZA runways, we can see that we've got just over 1,100. If we look now at our KZN runways, you can see that that's only 117. So we've clearly filtered the data at some level, all right? And, if we want to, we can immediately do a simple plot. This doesn't really help us very much. I just want to say that the reason that these are so small and faint is because it's trying to draw very short lines. The longest runway in South Africa is only about 3 kilometers long or something. So it's trying to draw very short lines, and because it's drawing all the lines individually rather than putting them as points, these come out very small. But you can see that we've now got something that's maybe workable. So, and to illustrate that even more, what we can do is we can take our ZA provinces and we can plot these, and we'll just plot them as light gray, and we'll give them an edge color because we're now dealing with polygons. Previously we just had lines, but we can give a dark gray edge color. And then what we will do now is we will plot our KZN runways. And in this case, what I'm going to do is I'll get back to this, but we're going to plot the centroid, which is the center position of a given geometry. for a point, it is the point. For something like a line, it will be your midway. And for a polygon, it will be the point that's sort of close, that is in the middle, rather than these tiny little lines above. So we're going to get the geometry, we'll pull the centroid, and we'll then plot that. You can't use columns now because we've pulled out only the centroid. Okay. So we want our base. We're going to use our base plot, and I'm just going to color these black. And we'll give them some transparency because they may overlap with each other. And for South Africa, what I'm also going to do is I'm going to set a limit in our Y direction. And this is because the shapefile that we import from Natural Earth includes the Gough Islands, where we had somebody apparently in the unsession on Monday, I think, was apparently on Marion Island, which is included in South Africa. So you can see that we have now gotten only the runways that are in KwaZulu-Natal. So this is useful. And I just want to emphasize again, or re-emphasize what I said earlier. We don't, the runways data frame that we imported has no idea what province it's in. Okay. So this is purely done by the fact that it is within another geometry. Okay. We could also work this in reverse using, for example, contains. We could give the provinces a particular runway and say, tell me which province this is. And it would come back and say, okay, this is in Gauteng or the Free State or whatever. Yeah. So what we've done, seem to have given this already. So what we can do is we can pull all of this stuff above, those individual steps, into a single function to create this rows diagram. We don't expect there to be any output from this because we're just defining the function. And we can now test this on the runways in South Africa. Okay, so, sorry, the runways in KwaZulu-Natal. So what we can do is we can call our rows diagram function, and we can say, okay, well, we want the KZN runways, and we're going to use the bearing for this. Okay. And the way that I've set it up, we can also give it a nice title. So we're going to say that we want the direction of KZN runways. Okay. And you can see that this is now very different to what our previous one had. There's a strong trend for northeast, southwest. There's a couple, and there seems to be something running slightly west of north as well. Okay, relatively few that are going straight east-west. Okay, if people want a bit of a break, but we can have a look here. It's fairly easy now to do this for each province. You could write some sort of you could write some code to generate us a rows diagram for each province, and you could then go and look at each province in turn. This is worth doing, but the idea here is less to work with basic Python and plotting, and I just want to give you an idea that you can pull these out. So hopefully you can see some uses. If you're a structural geologist and you've got, if you've got locations of dip directions or something like that, you could pull out for given geologies, you could pull out for given areas, and you can do similar things with, any sort of spatial data that you have. If you want to find out if a particular geology is present within a county, or, that sort of thing becomes possible. I see Chris was talking about doing wedge, or making equal area wedges for a rows diagram. This is just a simple implementation of a basic rows diagram just to get something working. There's definitely scope for saying that, or for looking at saying, okay, well, we actually want the areas of each to be the same, not just the height. there's issues with humans are very good at estimating certain things and poor at estimating others. And you can see that, for example, and the issue that is raised in the paper that he's linked here is that, for example, this here doesn't look like doesn't look very different to, for example, this one. So it's coming back to that. And definitely there's scope to improve what your actual rows diagrams look like, but this is just one to work with in the meantime. So I encourage you to give this a go. You'll get a bit of, you might get a better feel if you're plotting each province's runways and things like that. We can also flip this a little. So if we've got places in KZN, we can have a look to figure out, if there's interesting stuff related to those places. So we can again, this is pulled off OpenStreetMap. I've pulled out I think towns and cities, and we can see how these relate to runways. So one of the easiest things to start with is, okay, well, if we have a town, how many runways are within that? Okay. And what we can do quite easily here is, okay, I'm going to pull out a particular town. Okay, so let's work with Durban, which is KwaZulu-Natal's largest city. And we want that out of our South African places. And we're going to, from our South African places, we want to select where the name is equal to Durban. Okay. This should start hopefully looking somewhat familiar. And we can actually print out Durban's geometry just so we can see what we've actually got. And we can print out the entire data frame, in fact. So you can see that we have a point, okay, and it's of a D-type geometry. And here is the information that we have available here. We've got the geometry, we've got a founding date, which isn't given here, a postal code, an old name, if it's a capital, an ID, a population, I'm not sure when that was from, that it is a city, a name. There's already maybe something here where we've got an is in, but this is empty here, so it's not very useful. We know that it's a node and we've got some IDs. So something that's pretty easy to do is if we want to look at within a certain range, we can buffer. Okay, so in order to buffer this, we can take, I'm going to create a base axe of our project, of our province. Okay, and again, I'm just going to make this light gray. So this is going to draw our province boundary. We then want to have a buffer, so Durban, and it's very easy to create a buffer. It's already an existing function, and we can have a look here at what it does. So it returns a geoseries of geometries representing all points within a given distance of each geometric object. Okay, so in this case, we've only got one geometric object, but if you wanted to buffer, for example, all your roads by 50 meters, because that's the closest you're allowed to fly to them with a drone, or with a UAV, you can do that and you can say, okay, well, where are we safe? So we give it the radius of the buffer, and you can actually give it a series as well. So you could give different buffer. You could give a buffer for everything based on it. You could do some sort of calculation and say, okay, I want a buffer of 10% of the area, because that's the way that your wetlands need to be differentiated or something. And you can set the resolution. The default gives us a fairly nice circular thing, but if you want a square buffer for some reason, you can do that. Okay, so we're going to take the buffer. We're not going to do anything with it. We're just going to plot it straight. We're just going to take, we're going to give it a buffer, and we're going to give it a buffer size of 1, and we will plot it. And we'll use our existing base axe, and we will give this some transparency so that we can see what's going on, assuming I can ever spell alpha. So we'll give it some transparency. And just to show that this is around Durban, we'll just plot Durban on the same axis. And let's make it red. And just to make sure that it's at the top, I'm going to give it a Z order of 4. So the Z order basically controls the drawing order. A high Z means it's going to be higher up. This just forces it to sit above our buffer. And there we go. Effectively in one line of code, we've created a buffer around Durban. But we only said we want 1. Okay, so our buffer radius is 1. Now that's quite large for 1. So what we can do is, if we have a look at the CRS of this Durban geometry, okay, you can see that it is geometric. Okay, and that means that it's measured in degrees. Okay, so this buffer that we gave of 1 is a buffer of 1 degree. Okay. If you're doing measurements, if you're doing this sort of thing, often you'll want to be in some sort of projected CRS. You want to be able to work in meters, or I suppose if you're in the US and you're working with a county state plane or something, you'll want that in feet. And I see that there's been something yesterday. They were talking about redoing all the state planes, and Ohio has got something like 89, which sounds like a lot of different state planes for one state, but apparently they need that. So we should convert these to meters. Okay. I'm going to use the EPSG code for 3857. This uses meters but is worldwide. For our purposes, it's accurate enough, but if you're actually working within a well-defined area, you should probably use something that is better for that area. A good UTM, or often UTM is a good option. Some countries will have well-defined ones of their own. So there may be so for example, I know that the UK, they have a specific CRS that you can use. They've got a projection that works for the UK that they're happy with. Most countries will have their own. One limitation of the UTM projections is that they're best used within a particular width, and KZN is a little too wide to fit into one UTM zone. So I'm going to go for a worldwide one which uses meters as a unit of measure. So as I say, if you need to be absolutely sure that you are 50 meters away from your wetland, don't use 3857. But then if you're looking at a wetland, you're also going to be working with something that's much smaller and will fit into a UTM zone better, or into a state plane or something similar. So what we will do is we want to get our KZN runways, and we're going to get a projected version because we want these in meters. Okay, and this is as simple as saying we want our KZN runways, and we're going to give them a 2 CRS, and we're going to use that EPSG code that I gave up above, so 3857, and we're going to do this for the province as well, just so that we can keep plotting everything together. In practice, you may not need to do this. If all you're using 1.4 is as a plot, as a base plot, you could just use this KZN.2CRS underneath, and then when you do 2CRS EPSG equals 3857, sorry, 3857, you could just do that. So this on its own will plot whenever we need. You could use that whenever we want to plot it, but I feel like it's cleaner to be able to write KZN proj.plot instead. You just don't have to do the calculation every time. But for most computers, I think it's fine. And then we're also going to just reproject Durban to work on the same thing. And to be honest, the most important one here is that we get Durban, because that's what we're going to buffer. So hopefully this makes sense. As I say, I don't know how many people work with spatial data that often or try and do processing. So we haven't seen anything here, but what we do is if we copy now our same plot from up here, okay, if we take this plot here and we change all of these to our new projected versions, you can see that we can't see the buffer anymore. Okay, and the reason that we can't see the buffer is because we now have a buffer of 1 meter. Something worth noting as well is that this has changed our axes. Okay, so you can see that this is no longer in our nice degrees. This is now, 32, 3.2 million or whatever meters. Okay, but what we can do is if we change that buffer, oops, sorry. So again, taking this same code, we can now increase our buffer size. And, if we want 100, if we want a, let's say we want 100 kilometers. This, by the way, is something that I've discovered quite recently, just in case you weren't aware of it. You can put an underscore into a number as a separator, and that reads as a regular int. So if you're working with really big numbers, that might be actually quite nice to be able to split them up. So yeah, we want 100,000 meters because that's 100 kilometers. Okay. And you can see that we now have a 100-kilometer buffer around Durban. All right. And now what we can do is, since we have that buffer, we can select only the runways that are within that buffer, because that buffer has its own geometry. So we can, for example, do Durban proj dot buffer, and we wanted 100,000. You can see that this has a geometry. It's a polygon, okay, and it's got the various points that it needs. All right. So this means that, because remember that we were talking about with contains and within and intersects and things, it's comparing one geometry to another. We can use this geometry as what we're going to compare with. So, we're going to do this pretty much as we've seen. I'm going to, we don't need to save the Durban buffer as anything. So we're just going to go and we're going to say, okay, we've got our near Durban runways are going to be our KZN runways, and we want the projected ones. And we then want where these KZN runways, proj, we want to see where this is within, and this is going to be Durban proj dot buffer, and we want that 100-kilometer thing there. And just to be safe again, we're going to take it as a unary union just to make sure that everything works out nicely. So we've got one simple geometry. So we can't see anything because it's done something. But again, if we now look at near Durban and we check out its shape, we can see that we have only 31 features. So we've only got 31 runways near Durban. And this seems like pretty much exactly what we want. So what we can do is we can take our buffer, and if we have a look here, we've now plotted the centroids of the runways that are within 100 kilometers of Durban. Okay, and that is essentially the same code as we had. We're just now actually plotting the runways as well, these near Durban runways. Hopefully that makes sense. Hopefully people are following. Hopefully I'm not going too fast. The Slack channel on the Software Underground is open, so please do tell me if I'm losing you. So this is useful. I hope you can see where this would fit in. You can take your area and say, okay, give me things that are within a certain range of my area, or you can select within your area and say, okay, I'm pulling 300 well logs, but I'm only interested in the well logs within a specific box. And that box, as opposed to previously where we used the .cx and we selected by coordinates, where we had to now say, okay, well, we want a rectangle. Now we can have arbitrarily shaped boundaries. Okay, I mean, there's no easy way to express the boundary of this province in a simple call to a plotting function to say, okay, only give me the things within that, unless you're using something that is spatially aware. So you can do this in ArcGIS, you can do this in QGIS, you can do it in a script using Geopandas. Okay, and there are other tools that you can use to do this as well. So something that might be useful is nearest neighbors. Let's see what the nearest places are. We can get distances between things, because remember, we now have this geometry. And remember, we don't have distance calculated. It's not one of our columns. Okay, so just to remind you what's in these columns, we have, we can take our ZA runways, okay, and we can check out what columns we have here. And we've got a runway length, but that doesn't tell us if this runway is close to anything or how far is it from something else. Okay. Now, one of the ways to do this sort of thing, if we're trying to get distances, is if we've got two geometries, we can just use the distance. Okay, there is a method for distance, so we can take a distance, and it returns a series containing the distance to other. Okay, so what this means is that we can take, it's very easy if you've only got one thing that you're measuring to. So if you've got a geodata frame and you want to know, like, let's take these runways that we had, and we want to know, okay, well, what is the distance for our, and we'll do it on just the near Durban ones, near Durban, and we want the distance to Durban. I'm not sure if we need to give that a geometry. I think we need to give it a geometry. And we want that, so you can see that it's complaining because it's not reprojected. So it may work. Oh, reproj. That should not be nothing. Sorry, give me a second here. So for distance, do I need to give it either the geometry or the not geometry? That should be giving us a sequence back of how far we are. I'll have to double check. I'm clearly using this wrong. I apologize. But in any case, we can get these distances between things, because I'm about to do that and it was working. So if we want from one point to all, or from all our points to one point, that's not too bad. But if we wanted for all of them, what we need to do is we want to apply things to our various, we want to be able to apply them. So we can, and in order to apply, you need to have a function that you can use. So I'm going to define a minimum distance function, which is going to take a given point, and it's going to take a destination point. Okay, and that's exactly what we're going to tell it that it does. It takes a point and destination, expects to be in meters. Okay, and what we will do now is we can simply return the destination and we can take the distance. Oh, I've gone the wrong way around, that's why. I just realized where I went wrong. So if we take, well, I hope I realize why I went wrong. If we take Durban distance and we give it the near Durban, no, still not. Not sure why that's coming back as nams. Makes me worry that this isn't going to work. We can take the distance to our point, and we want the minimum. Okay, because remember that with a point, our points are possibly going to be whatever they are. They may not be the closest. We just want to explicitly say that we want the minimum here. And now what we can do is we can use the apply function again, and we can say, okay, let's take our Durban proj, and we're going to take the geometry of our Durban projection, and what we will do is we will apply our minimum distance function. And I'm not entirely sure why, but it is important that you give it these arguments that this is or these are the, sorry, it's not that I'm not unsure why it's important, but what it is this is the argument that gets passed in addition to the one that you're already passing. So the first argument will be this Durban projection, which will be the point, and then our destination is going to be all the near Durban geometries. And this isn't working because why? That is strange. This was working, I'm sure. I should have tested everything. I apologize for this, folks. If anybody in the Slack chat has an idea here, because it should, so it's a truth value, so that means it's trying to apply it to everything, which doesn't quite work. Sorry, live debugging is not necessarily what I was wanting to do here. I will try reloading some things. Maybe I have gotten maybe I've messed up with one of the projections or something, but it should be fine. So we can read in our runways and our provinces. And then as we go down, what we will do is, we haven't done any, we will need to maybe just reselect our South African, our KZN runways. And we want the projected versions. And do we have places? Where did I import places? That was here. We can import our places. And we should just then redo that projection of KZN places. Oh, we haven't done that yet. Have we? No, we haven't. Okay. So hopefully this works now. Sorry, folks, I really don't know why this is complaining. It's I know what it's complaining about. I'm just not sure. Every time I get it, I can never remember exactly how to fix it. I apologize profusely for this, because what this should be giving us is it should be giving us the minimum distance between each point. Oh wait, maybe that's that comma that I was. There we go. Okay, so the problem is that that comma after near Durban is important. I glossed over that there. So what this is telling us, apologies for all of that, what this is telling us is that the closest runway to Durban is 12.25 kilometers. I see Lewis has just gotten it as well. Okay, so what this is, so what this tells us is that the closest is what the closest distance to our geometry is 12.25 kilometers. And remember that we've given it a projection in meters and it's come back out and we've divided it by 1,000 to get it into kilometers. You could give this something else. So if we gave this our unprojected data in WGS84, where it's working in degrees, it would still come back as it wouldn't complain, but we'd be getting very small values. They'd be very unusual. It's not really sensible to try and measure distances between things using degrees. Okay, so what we can do is we could also pull out a specific town, or we could pull out a runway. So we can work, okay, so here's a particular runway, and I've just used the OSM ID for this. And what we want is we want to try and get the minimum distance for that. So pulling out this particular runway, we're going to use that similar pattern to what we've seen. We want, actually we're not sure if this is in, this could be in anywhere, but I know that it's in KZN. So we'll pull our KZN runways and we want where the OSM ID is equal to, and I'm just going to copy this. So where that is true, okay, that is we're going to select that from KZN runways. We could save this as a new runway, and I think I'm going to do that. So that specific runway there. And then what we can do is we can do the same code that we used above in here. We're going to then take from here, we're going to use its geometry, and we will then apply our minimum distance, and we will give it the args that we want. And what we're going to do here is we're going to use the ZA places. So we're going to look for the closest town in the places thing. And because places is not projected yet, we need to do a 2CRS. And we're going to use the same EPSG code here that we used earlier. So 3857. And let's not forget the comma this time. And that is coming back as blank because why? This section seems to have gone a lot less smoothly than I was hoping for. That should be coming back with a value for us, assuming that the runway exists, which it should do. No, that runway code is not coming back correctly. So just so you can see here, the runway is empty, which means that the answer we're getting is entirely sensible. If that runway isn't there, then it obviously can't match on anything. And we can have a look at what runways we want. So let's just have a look. I'm going to just pull a different OSM ID and hopefully this works. No, it's still coming back as empty for some reason. I'm not sure why that should be. So it's all coming back as false. It could be because it's a string. Data type strike again. Okay, so we're going to then just and in this case again we're going to give it all of our ZA places and we'll do a 2CRS EPSG 35 3857, sorry. And now we get an unexpected end of file because of what have I done this time? This is not going as well as I'd hoped. Oh. No. Oh. Okay, and that tells us that for 6211489, the closest runway is just under 4.5 kilometers away. And yeah, Matt, I agree. That is one of the annoying things that with pandas is that it's not always entirely obvious when you simply do something like this, whether this is a string or an integer or what. It's usually been fairly sensible about deciding that something is an integer or a string, but in some cases that doesn't work out. And yeah, showing something in the header that this is a string or this is an int, just the D type in the series would be a very nice addition to the thing. So yeah, sorry about that. This is how it goes sometimes, I suppose. I was hoping that I was a bit more prepared than it makes me look like I am. So yeah, this is a easy or a relatively easy way, once we worked out all the bugs, to get to our nearest neighbor. We can now find the single thing that's closest to where we are. It doesn't really make much sense, but you could quite easily reverse this and say, instead of giving me the minimum, give me the maximum. You can find the furthest neighbor, for want of a better term. But using this distance, you can actually then figure out where you are, and you can do some of these measurements. Again, you need to make sure that you're using compatible CRSs as well. Okay. So here we've used it. So something else that we may want to do is use it on multiple features. So instead of finding the nearest neighbor of just from Durban, we can take our nearest neighbor to every town. We can figure out which runway has, for each runway, we can see this is the nearest town to it. So I'm going to start off by selecting only the places in KwaZulu-Natal, and within KwaZulu-Natal, we're then going to just reproject that for ourselves. Then, yeah, Jan. Yeah, I mean, having a few issues here and there is, I don't know, I suppose it shows just how little ahead I am, but you can definitely do cool stuff even if you're stumbling, as long as you are. It really helps to have a group of people hanging around looking over your shoulder to say, this is where you went wrong. So yeah, and the Software Underground's a really good place for that. If you do get stuck and just can't figure out why something's not working, somebody may know that you need to put that comma inside there. I remember it took me a while to figure that out in the first place. So, but memory fades quite quickly. So what we've got now is we've got the places in KwaZulu-Natal, and they're in our distance in our projected coordinate system, so we can use meters. And what we're going to do now is we're going to plot the centroid of the runway, and we can see our places in relation to where the runways are. So in this case, the runways are the blue dots, and the little crosses are our places. So what we can do now is, if we use the apply function, we can apply it on the entire data frame, and we'll get a result for each of the features. So what we're going to do now is we're going to get a minimum distance to place, okay, which will tell us what the distance to the nearest place is, okay. So you can see here, if we look at the description, most of our runways, okay, our mean distance is just less than 19 kilometers. The furthest you would have to get to a runway is 67.5. And to be clear as well, these are runways that have been drawn in on OpenStreetMap. They may not be actual runways. They may just look like runways from the air. It doesn't mean that you've got anything serious in terms of being able to fly a large plane in and land it. These might be bush strips or a runway on a farm or something like that. So yeah, what we'll do now is we'll plot the runways, and we can have a look at their geometries. So what I'm doing here is, again, coming back to the centroid, okay. What this does is it finds the stuff that's in the middle. I'm saving the line geometry in a column, okay, and then I'm making the geometry of the thing. By default, pandas will look for this geometry column, okay. So I'm then forcing that geometry to be a point. It just means that instead of plotting centroids, I can plot the actual data. Depending on what you're trying to do, here is, you may or may not want to do this, because you are now altering your data. So just, if you're doing this for something critical, you may not want to do it. But one of the problems is that when you call these centroid, when you say that, okay, I want, ZA runways dot centroid, okay, because you're getting back a series, you don't have access to all the features that you may want. So you don't have, so because you've only got these normal, you've got a lot of functions available, but they're not necessarily the ones that you want. So whether you can pull out, for example, I want the centroid for a specific column, I don't think really makes sense. So if you're trying to then do a centroid plot, and actually I don't think I even tried this, I think I just assumed it wouldn't work. So, let's just give it a go. In the spirit of mistaking, let's see if that works. Okay, so you can see that this doesn't work, and maybe I did try it, but you can see that the path collection property has no object, has no property column. It doesn't pass the column through from the centroids. So if you're wanting to plot centroids specifically, you're going to need to make a new object which has them as centroids. Okay. But now that we've changed our geometry, we can now use our normal columns and everything, and we can now do whatever we would normally do. We can plot our minimum distance to a place. In this case, you can see that I've gone with an equal interval, and I want 7 gaps. Okay, we're plotting a legend. This is all stuff that we've seen, and then we're adding on top of this, we're adding the places as little red crosses. So you can see in terms of distance to runway, roundabout St. Lucia is probably where you don't want to be. Okay, so here are where you're furthest from a runway. You've got a couple places that are basically right on top of a runway as well. So And what we can do, I think maybe I'll give people a couple of minutes just to assimilate, and if there's anything, also for me to reset a little from the wobble that I had just now, um, would be to have a look and see if you can, now that if you can figure out how to plot the different towns and cities colored by distance from Durban. So this is using what we've had above here. We can find that minimum distance, or we can find a distance. And if we've got that minimum distance, we can then, get a color gradient and say, this is how we're going from Durban. So yeah, let's see. It's 10 to the hour. Let's give it 5 minutes, so that we come back, and we'll start with that. We're nearly done with this notebook, so I'll give that a go quick. We can do that, and then we'll figure out how to get more information than just the single value, which will be quite valuable. Okay, but let's stop there for now. Give it 5 minutes, and then yeah, I'll be over in the Slack if people want to talk about any of it. Cool. So what we want to do, as we said just before the break, is we're going to try and plot the distance, or we're going to try and color the distance, the different towns and cities, and we're going to look at doing it by figuring out how far they are from Durban. Biggest city in the province. That might be good to know. So first of all, what I'm going to do is I'm going to keep a copy of Durban. Because we're going to be adding data to this, and I want to keep my original one here. So what we want to do is we want to take our KZN places, and we're going to make a copy of this, so that when we write stuff to it, we don't need to then go and drop these columns later. If you're doing an analysis and you're going to save things, you may not want all of the intermediate steps. So you can create a copy, do some stuff, and then write the final values or whatever. But so that's just something that you may want to consider. We're going to add a column called distance Durban. And the reason to do this is because if you were going to then do this on 3 or 4 different towns, you may not want all the towns in there, for example. And we'll do more or less the same as what we did just now. We're going to take our KZN places. We're going to grab their geometries, and then we're going to apply our minimum distance function. And our args are that we're going to do this with the projected Durban data. Okay, and then we've got that. And then we can start building up our plot. And again, this is fair. There are some options. So when you're plotting this sort of thing, there is something else that you could use called Geoplot. I found that it's got some annoying restrictions on what it can plot. There's certain things that it's really good at doing. You can just plot it immediately and it looks nice. But as soon as you're trying to tweak it or you're trying to get different things, I found that it was a little bit more limited, which is why I haven't really gone over it. If you're looking for doing stuff with a lot more flexibility, I would suggest sticking with CartoPy as your plotting thing, or use this matplotlib interface. Okay, so we're going to plot KZN, and we'll put a boundary color on it. So the edge color means that we will color in the line on the outside as well. And then we're going to take our KZN Durban, and I'm going to do more or less try and do this all in one go here, because we've got our KZN Durban, we've got sorry, I'm not doing it all in one go. We've got our distance to Durban, so that's going to be the column that we want. Again, we're going to give it that ax that we want, so we've got it, put it on our base ax there. Our column that we care about is that one that we've just calculated, our distance to Durban. We're going to use some sort of scheme, because what we're doing is we're dealing with data that runs over a range. We don't necessarily want it continuous. We want to block it up a little. So in this case, I'm going to use one called one of the Jenks schemes. So Jenks Caspel Forced. And we're just going to split it up into 6. If you were interested in the exact distances, you can do that. But often if you're trying to actually figure out which point belongs to which range, it's not that easy. So sometimes it's just better to bin the data like this. And we can do it with, let's make them red. And we're going to use the reverse one because we want it to be, because of how we're wanting to set things up. And as a marker, we'll just put it as that. And just so that we know where it is, we're going to plot Durban as well, again on the same ax that we were using, and we'll make it red. So this should mean that as you go further away from Durban, things get lighter, which is indeed what we get here. Okay. So you can see that we've got our Durban, and it's binned it for us. By looking at the map classify stuff, you can get a better idea of how it's binning and what the binning options are. But you can see that the furthest places are between, call it 250 and just over 400 kilometers, and they're all up north here, which makes sense. And you've got a bunch of places that are much closer, less than 20 kilometers. Now, as I said, so far we've only gotten the distance to the nearest neighbor, but we haven't gotten anything else useful from it. So what we want to get the entirety of the geometry as well. Okay. So if we import shapely op, or from shapely.ops, we can get these nearest points. Okay. And from there, okay, and we can have a look. I'll pull this out and we can see exactly what it does. So we can have a look at nearest points. You can see that it returns the calculated nearest points in the input geometries, and the points are returned in the same order as the input geometries. So what that means is that we're going to get multiple points back. Okay, so for a row, we have whatever we're interested in. We're then going to get a destination, and you give it the entire geodata frame. Okay, one of them is going to be the closest. We don't know which one yet. Then coming back, we're going to get the value of the column containing the values which the destination gives back. And then, yeah, in this case, we can change it if for some reason your geometry is not actually geometry. So stepping through this, we're going to combine our geometry into one thing. So it's a unary union. We've seen this before where we can now, instead of dealing with multiple parts of it, it all becomes one object. I should also point out here that it becomes one object, but it's not, it doesn't become one object in the fact that it fills in the gaps. It just gets treated as a single object. Okay. Then we're going to get our nearest points. Okay, so what we do is we give it our row and we say, okay, if we've got a different geometry, we'll use that. And we're going to then give it the union of all of the destinations. Okay, and then we match it and we look for the nearest geometry. Okay? And what we can then return is that match value. Okay, so we can ask for specific values of the nearest object. Okay, we don't know. So, for example, if you wanted to find the length of the nearest runway, okay, you can do that now, because what it's going to give us back is the value of the match that is the nearest object. Okay, hopefully that makes sense. If I'm a little bit unclear, let me know in the Slack and I can go back on it. But what we're looking for specifically is we're looking for the value of the nearest object, and we're looking for a value in a specific column. Okay, so we can get, for example, the name of the nearest place to each runway. Okay, we've already got the distance from each runway to the nearest place. Okay, but if we want now to take where we've got these nearest things, so we can take our calculate nearest, we're going to apply that. We're going to say that our destinations are all these KZN places. We want the name, and we're doing it on axis 1. You can change this axis where if you're wanting to find things slightly differently. I can't remember exactly why we needed this, but and we're going to save that as the nearest place name. So what this means is that each row, when we're done, is going to be, each feature will now have an additional attribute, which is the nearest place name. Okay, so when we run, I need to run this cell. So as expected, we don't get any output. But if we look at the nearest place name, we can see that for the first 10 things, we've got Newcastle, Ladysmith, Chatsworth, Richards Bay, Durban North, Jazini, Tongaat, Vryheid, and Underberg. Okay. And we can now plot these because this is just another column. It's another attribute that we can use. So again, this should be fairly similar now. That fig size is maybe a bit too big. We'll stick with our standard 8x8. We're going to plot. We're going to plot our thing out. We'll put our background in as usual. We'll plot all our places in black as a black cross. We're going to then color by the nearest place name. And these are major places. So, I mean, there's other stuff in between. And I'm just going to put some bounds on it as well. I think that was me playing around with trying to get certain things working. But now what you can see is that we've got a variety of colors, and these over here are closest to whatever that town there is, which should be Vryheid. Okay, the colors are maybe a little bit difficult to see because there's actually quite a lot of classes in this. You wouldn't necessarily want to do this with as many different values. But in general, I hope you can see the application here. You can now find out, for example, if you have a injection well, you can see okay, give me back the production value after a certain amount of time. If you've got that as a value in your other thing, you can say, okay, give me back the production value closest to this. Give me the or if you're dealing with something that's maybe on a borehole log, you can say, okay, well, find me the deepest borehole log that's near here because I've only got time to really log one. Or, there's stuff like that that you can start doing. And the important thing here as well is that because we're looking at these in a spatial context, we don't need that data to already exist to tell us, oh, the closest borehole to this is that. Okay. So you'll have to, working with this particular function, you'd need to figure out what you're actually wanting to get back, but it is possible to get back any particular column. Okay. And I think this is a hangover from earlier. Oh no, it's not. It is new. Okay. So what we can do is, I'm not going to do the first one. We've done plenty of that already. This is just, color it by bearing. I feel like we've seen enough of these basic plotting functions that I hope you're getting fairly comfortable with them. So now what we'll do though is I'll do the second one here where we can combine a few things together and we can sort of pull out all of the ones, and it's very similar to what we've done before. So what we can do is we can pull out Pietermaritzburg and we want some sort of buffer around it. Okay. And we can do this in one go because we don't really need Pietermaritzburg in itself. So we'll use the projected KZN places, and we want that where the name of this place is Pietermaritzburg. Okay. We want to use this as our, that's going to give us a Boolean series back. So we only want it where it is true, where KZN, so we want where our KZN places, where these are coming true as it is equal to Pietermaritzburg. And then we want a 150 kilometer buffer. Okay. Then what we want is we're going to plot the KZN runways. Okay. And what we're going to do now is I'm going to mix it up a little. I'm going to do this all more or less in one go. We want these KZN runways where they are within our Pietermaritzburg buffer. Okay, and we're going to just make sure that that all works together. So we want that as a unary union. Okay. Again, we're going to select where these are true, okay, from our KZN runways. And we will then plot that. And in this case, because I'm just going to make it as simple as possible, we're just going to plot this by length. We're not going to add anything extra. And you can see here that we now have a plot of, okay, again, there's no real context. You can't see where this is. We'll get to how you would add, for example, a base map onto this later. But this gives us now our runway lengths. You could add a legend, you could bin this. You can see that there's one particularly long runway and one that is slightly shorter, and then most of them are pretty short. For what it's worth, this is King Shaka International, and this is the old Durban International Airport. So that makes sense. These are our big ones, and then this is Virginia Airport. And Pietermaritzburg is a little bit inland, and there's a whole bunch of little farm runways and things that have been mapped as runways. Whether they're entirely runways would need some ground truthing. But yeah, so this finishes off this one. Are there any comments regarding what we're doing here? As I say, I think it's worth reflecting on the fact that most of this stuff is actually spatially oriented. You don't need to have a column saying that the runway is within 150 kilometers of Pietermaritzburg. You can do that afterwards on its own. You can say, okay, give me a buffer of 150, and you can select the stuff that's within that. You can do that with whatever data you have available. And you don't have to then bloat your initial data by trying to accommodate everything. You don't have to say explicitly that it is within this province, it's within this county, it's within the city limits of this. You can pull that sort of stuff out later, almost on the fly as you go, by saying, okay, give me everything that's within the city limits of that. Okay. I think we're doing all right for time, so I'm going to go through the joins and spatial joins bit fairly notebook as well. This is really useful. It becomes very useful if you're working with databases and things as well. But if you've got two data sets, you might only have the you might only be yeah. So if you've got two data sets, you often want to relate them to each other more directly than what we've been doing. Are we over time? Oh, we are over time. Whoops. Okay, never mind. Sorry, I'm getting myself confused. I'm not going to do the spatial joins then. What I'll do is I'll finish with something that's just nice. Okay, and this is to get some base maps. Okay, these are not going to be interactive, but they use a library called Contextly or Contextly. Again, we can read in some data. This is mines in Tanzania, and you can see that we've got a bunch of stuff. Now, we can plot it as normal, but this doesn't really tell us very much because we don't know what we've got. We can give it some more context, though. We can use Contextly to give it a base map. And this will take a while to run the first time because it's got to fetch the tiles, but it'll cache them afterwards. And once this gets through, once this downloads, we'll end up with a much nicer base map. The base map is automatically projected as well, which is nice for us. So we can use the base map and it'll immediately just say, oh, it's here. Okay. I think I'll probably cut it. If we're already over time, we can cut it. But you can see how in one line of code, or two lines of code, we've plotted our data by the type of mine or the type of economic activity, and we've got a base map sitting there underneath it. Okay, and you can see that it's reprojected. This is not a standard web map that we're using. It's using what we've given it already. So we've got it in a UTM zone based on ARC of 1960. Okay, and if you reproject your data first, you can get that much back. You can now put that into degrees and latitude. There are a bunch of different options for base maps. So you get base maps from a bunch of places. Some you'll need to actually have an API key or something similar, but it's quite easy to change them. I'm just going to go through to the last bit, which I think is really cool, where you can you can use geocoding to find specific places. So, for example, you can download the place, Paraguay, okay, and the tiles that it will use will be the Esri Delorme style, okay, and that's very easy then. If you've got existing data, you can put that underneath something. So you can see that we've got Paraguay, we've downloaded one tile at Zoom, and we've gone to Zoom 7, and that's sort of the size that we're working with. The zoom levels can be set, and you can tweak these a little. But you can see now I've plotted them in red because it shows up better. But here are a bunch of rivers in Paraguay, and we've got a base map. And I haven't needed to try and figure out the areas or anything like that. It's very easy to do this with more or less anything that the GeoPlaces geocoder can find. So if you want to, here's where I would definitely encourage you to find your nearest place or a place that you know, and you can very easily drop this in as a base map underneath an existing plot. You may or may not, if you're looking for very small things, you can set the zoom level. Some providers give a list to Zooms, to how far a Zoom can be. So yeah, this one is an interesting set of things that you can do with. It doesn't give you interactivity, but it does give you much prettier maps. Um, and I think that that's more or less it then. I would encourage people to have a look through the joins and spatial joins. If you want to talk about it, I'll be in the Slack channel. I mean, I'm in Slack fairly regularly anyway, so feel free to ask me about any of the stuff that I've done here. Yeah, there's a couple people to thank, Matt, for producing this. Definitely everybody who's been involved in the organizing of Transform. Thanks to all the people hanging around in Swung in general and the guys who engaged this morning specifically. Thanks for joining. As I say, I hope that this gives you some useful tools that you can use going forward. Some ideas for putting into workflows where you can do some cleaning before you put it into ArcGIS or whatever. Um, but yeah, thanks very much for joining. There are still a couple of other things here, but happening later on. There's some more lightning talks, which will be cool. And there'll also be the MVP discussion. But this will be archived. So yeah, I'll see you in the future, or you'll see me in the future. Thanks very much for joining me.